Welcome back. Today we're going to look at finding some integrations using some basic methods, U substitution, which you likely were introduced to in Calc 1, and then some other basic types which might involve taking some, using some algebra or manipulation of the integral that leads us to something that we can actually solve. So let's just jump right in there and look at some more examples of these things. All right. So let's start with one like this. Antiderivative of 7x plus 4 to the negative 10 dx. So we would like to use a U substitution to solve this. What I'm going to do is I'm going to let U be what's inside the parentheses. Remember that we're generally looking at parentheses, exponents, denominators. Those don't always work, but that should be your first try if a U substitution is going to work. So we'll let U equal 7x plus 4, so that the derivative is 7. du dx is 7, derivative of this is 7, but remember how we write it when we're making a U substitution for an integral. We're going to think about bringing the dx over to the right, so that du is 7x dx. We need to convert everything in our integral over to U. This is U to the negative 10. We need dx to be gone as well, and it also needs to be in terms of U. So what I'm going to do is I'm going to insert a 7 so that I get 7 dx, just like we need. But by doing so, I need to remove that 7 outside of the integral. And now, this becomes 1/7 integral of, this is U to the negative 10, and 7x dx is du. This only works if it's a constant, right? I can't input x and divide by x. That's no good. You can't bring a variable across the integration, but a constant does. So this will work anytime your derivative is there up to the constant. Antiderivative of U to the negative 10 is U to the negative 9 divided by negative 9. We go up, right? Up from negative 10 is negative 9, divide by the new exponent. The 1/7 is still there, and then plus c. So this is negative 1/63 U to the negative 9, which is negative 1/63. We need to convert back into x. U is 7x plus 4, so 7x plus 4 to the negative 9 plus c. And there we have it. Let's look at another one. Okay. How about cosine 4th x sine x dx? Remember what cosine to the 4th x means. It really means cosine x raised to the 4th power. That's what it means. So if we're going to use a U substitution, our first things to try should be what's in the parentheses, what's in an exponent, what's in the denominator. Well, this is what's in the parentheses. Cosine x is what's in the parentheses. And we're going to try that. If U is equal to cosine x, then the derivative of cosine is negative sine dx. Remember, this is how we write our derivatives when using when using U substitution. This is good because this then will become U raised to the 4th power, and the sine x dx is essentially what I have for du. Although just with the previous example, I need negative sine x dx, so I'm going to make that a negative sine x by putting a minus in and taking a minus out. And after I do that, that becomes negative U raised to the 4th power. This whole thing is du. So du. Integration of U to the 4 is U to the 5 over 5. Put U back into x, and I get cosine 5 x over 5. And that's our answer. Let's do another one. E to the 3x over e to the 3x plus 4. Okay, remember, exponents, parentheses, denominators. The exponent is actually not going to work here for a u substitution. If u is equal to 3x, then the derivative is 3 dx. That would be fine. The dx is okay, but this would then simplify to e to the u over e to the u plus 4, which doesn't lead me to anything that's actually easier to integrate. But if we try the alternate idea, which is to let it be the entire denominator, e to the 3x plus 4, we'll actually find something that works. If u is e to the 3x plus 4, du, derivative of e to the 3x, is e to the 3x multiplied by the derivative of the exponent, which is 3. So 3e to the 3x. The 4 goes away when taking the derivative. So du is 3e to the 3x dx. Which is good, because what I have right here is e to the 3x dx. So I can almost make that into du if I have a 3. Well, at this point we know what to do with that. We put a 3 in, so that this is now all du, but we have to divide the 3 out. And now we get 1/3 integral, the numerator is du, the denominator is u, e to the 3x plus 4. So du over u, which is 1/3. This du over u we're going to see a lot, and it's just, you have to just get comfortable with it. It shows up all the time when we're finding these antiderivatives. This really is 1 over u du. If we just think about some algebra there, that's 1 over u du. What has a derivative of 1 over x? ln has a derivative of 1 over x. So this is 1/3 ln, remember the absolute values in this case, 1/3 ln absolute value of u. We can't apply the power rule. This is u to the negative 1, but the power rule doesn't work because it would be u to the 0 over 0. Can't divide by 0. This is just a unique situation where the antiderivative is ln. Finally, we have to turn u back into x, so this is 1/3 ln absolute value e to the 3x plus 4 plus c. Let's look at another one. ln x over x. Alright, there's no exponents, there's no parentheses, there is a denominator, but if I let u equal x, then this is just ln u over u du, and all that you've done is change the variable to a different letter, and it looks exactly the same as far as finding the antiderivative. So letting u be the denominator also doesn't work. So I can't let u be x. There's no exponents, there's no parentheses. If the u substitution is going to work, the only thing that it could possibly be is u is equal to ln of x. And we'll see that this is going to work, because if u is ln of x, du is 1 over x dx. And 1 over x dx is what I have right there. That's 1 over x multiplied by dx. So this box is now du. ln of x is u. So we get integral of u du. This is u to the first power. The power rule does work here. And I get u squared over 2 plus c. Finally, return u back to x. U is ln of x, so that is ln of x squared over 2 plus c. Keep going. sine squared. Sine squared. Integrate sine squared. We'll find here that no u substitution is going to work. There's really only a few options if a u substitution were to work at all. I could try u equals sine x, but if u is equal to sine x, du is cosine x. And there's no way to make du show up in there because there's no cosine. So that's not going to work. The whole thing is sine squared x. If u is sine squared x, then this is like sine x squared. So the derivative is 2 comes down. Derivative of the inside is cosine x. That's also pretty complicated, and there's no way to get du up into our integral. So that doesn't work. Those are the only possible things that might even work for a u substitution, so it's none of those. A u substitution is not the way to solve this problem. What we have to do is remember a trig identity, which is going to allow us to remove the exponent. And here it is. This is a double angle formula. It takes an exponent and turns it into double the angle, right? So the cosine of 2x. There's a similar one for cosine squared, for cosine rather than sine, where it's 1 plus cosine 2x over 2. So these two are identities that we're going to have to use in the future, so keep them in mind and put them in a safe place. For right now, we just need this top one. I'm going to split that into 2 pieces. So that when I sub it back into the integration, it becomes integral of 1/2 minus cosine 2x over 2. I can integrate 1/2 and I can integrate this separately. A constant integrates to the variable. So this is 1/2 x. I'm going to think about this 1/2 as out front and then integrating cosine of 2x. Cosine integrates to sine. That 2 is a little bit of an issue, but let's think about how it's going to work. I could actually, if I wanted to integrate cosine 2x, I could actually let u be 2x. I can make a u substitution with u equal 2x. So that du is 2 dx. Which means that from all of our ideas from before, if I want to get du up in here, I'm going to put a 2 in, and I can divide a 2 out, so that this integration becomes 1/2 cosine u, integral of cosine u, times du. And then cosine u integrates to sine u, but u is 2x. So this is 1/2 sine 2x. So cosine 2x is 1/2 sine 2x by that u substitution, right up in here. I still have the 1/2 from before that was outside. I have the 1/2 x from before as well. Plus c. So put this all together and we get 1/2 x minus 1/4 sine 2x plus c. So there was a u substitution, a minor u substitution as a part of the solution, but the key point was to break this up using a double angle formula. Alright, we're going to do one more. What I would like to do is integrate x plus 4 over x squared plus 1. Again, a u substitution is not going to work, because if u is equal to the exponent, or there's no exponent, if u is equal to the numerator, x plus 4, derivative is dx, but I can't do anything with the x squared. if u is equal to the denominator, x squared plus 1, derivative is 2x dx. I don't have 2x dx. And I can't put 2x in because I can't remove it I can't let an x out on the outside. So, so what I actually have to do is apply a little bit of a clever algebra trick to make it work. First, I'm going to break this up into two pieces as follows. Okay. This is really just backwards from getting a common denominator. The denominators here are x squared plus 1 and x squared plus 1, so I could put them together and get x plus 4 as my numerator. This left-hand side I can actually solve by using a u substitution now. Because I broke it up into two different pieces, if u is x squared plus 1, then du is 2x dx, and now we've seen this 10 times. This is x dx. I can make it 2x dx so that the integral is 1/2 integral of, this is du, and the denominator is u. Du over u, we've actually already seen as well. That's 1 over u, du. 1 over u integrates to ln. So that's 1/2 ln absolute value of u. But u is x squared plus 1, so that's 1/2 ln absolute value of x squared plus 1. The right-hand piece we have to do differently. I'm going to first pull the 4 out and think about 1 over x squared plus 1. 1 over x squared plus 1 is something we have to remember from Calc 1 as actually being an inverse trig function. There's two that we're going to need for this class that we're going to see in the future, now as well as the future. Integral of x squared plus 1 dx is tan inverse of x. And integral of 1 over root 1 minus x squared is sine inverse of x. So these are the two that we're going to see right now, and then also in a little bit in a few sections ahead as well. They are something that you probably saw a proof of or a development of this formula in Calc 1. I'm not going to do it again right now. Actually, it's very similar. It follows exactly the same pattern as we used to find the derivatives and antiderivatives of the hyperbolic functions by using implicit differentiation. It's really almost exactly the same process. But by doing so, 1 over x squared plus 1 is tan inverse of x. This then is 4 tan inverse of x. So the final answer will be this and this. So 1/2 ln absolute value of x squared plus 1 plus 4 tan inverse of x plus c. And so it's a little bit of a clever algebra trick that makes it work. We break it up into two integrals. They look pretty similar. One has an x in the numerator, one has a 4 in the numerator, but we have to apply very different thinking in order to get the antiderivatives. A u substitution works for this one. This one is just an inverse tan function. And so we get a complicated looking antiderivative, but it is the correct answer. All right, I'll see you next time for integration by parts.